Hey guys, welcome back to the Biomechanics 1 video series. In this particular video series, we'll be looking at concepts of angular momentum and moments of inertia. So just to highlight, in previous videos we learned quite a few things, right? We learned that an object that is rotating about some axis will experience some kind of linear velocity that is typically tangential to the path that it is traveling. Right, so for example, this object will have some kind of velocity as it is rotating about some axis, and that velocity will be tangential to its path. So when this object tends to rotate to this point over here, let me kind of just demonstrate that for a second. So when it rotates from where it is currently to over here, for example, then its velocity will still be tangential to its path, right? Okay, so that should be fairly straightforward. We said that the velocity that an object will have is dependent on how far that object is from some axis of rotation, right? So we denote that by r and say, well, this object is a given distance from this axis of rotation, and the velocity that it will have is related to how far that object is. So if the object is closer, its velocity will be smaller. Right? If it's further away, it will be larger, and it was linked by this specific formula saying that the linear velocity is equal to the angular velocity times the radius, where the angular velocity is the distance, the angular distance through which it rotates, which is measured in radians, right? So angular velocity was the number of radians through which it rotates in a given time period. Right, so the change in radians over the change in time. So that's just general revision. The other thing that we learned is that when I apply a force to a rotating object, or to an object that is fixed about some axis, it will tend to cause some kind of rotation. So if I apply a force to this particular object, and given that the object is some distance from an axis of rotation, that's known as a torque, where torque is equal to the force that I apply multiplied by the distance from the axis of rotation where I tend to apply that force. Alright, so this object will start possessing some kind of momentum. When we spoke about linear momentum, we said that linear momentum is equal to mass times velocity, right? So there should be some kind of angular equivalent to that, and that angular equivalent is called angular momentum. So where angular momentum is denoted by the letter L. In some textbooks it's denoted by the letter H, but for our purposes we'll be using the letter L, and it is defined as mass times velocity, right? Exactly the same as what the linear component is, but if there was nothing else to it, it would just be linear momentum. So the component that we add to this is r, where we say that the momentum that a rotating object will have is dependent on the distance from the axis that that particular object is. So we would have a problem if this object was anything else than just this kind of point mass. If it was maybe like a long bar, the mass is not equally or mass is not uniformly distributed at a given distance. In this case, all the mass is located a specific distance from the axis of rotation. But in something like a bar, if it were rotating around the endpoint, notice that this bar is made up of mass all along its length, right? So that would make this calculation a little bit complicated, because I'd have to check each individual bit and say, well, what is this individual mass of this bar? What is its distance from the axis of rotation? And then if I take this little piece of mass and it's got a different distance to the axis of rotation, I've got this little piece of mass and it's got a different distance to the axis of rotation. I would have to sum all of those up to try and get an idea of what its angular momentum is, right? An easy way around that is, since this object would still be rotating, if I just take its angular velocity, then all points on this object would be rotating with the same angular velocity. Well, luckily for us, there's a formula that we have that allows us to express angular momentum in that particular format. So instead of having velocity in this format, I'll simply replace it with this particular concept. So my formula will look something somewhat different, right, where I'm just replacing the units of velocity with this angular velocity times r. Alright, good. So if I multiply this out, I will have m times angular velocity times r times r. Well, I'm going to simplify that a little bit further and just write it before this angular velocity component. So just get this mr squared times angular velocity. Okay, so this mr squared gets given its own symbol. It tends to come up quite a lot, and mathematicians are quite lazy, so whenever they see something that tends to come up quite a lot in different formats, they tend to give it a new letter. This is ascribed the letter I, which refers to the moment of inertia. That's kind of like the official definition of it. You could also think of it as the rotational inertia, and I'll kind of explain why that is the case just now. So in essence, mr squared is called the moment of inertia multiplied by angular velocity. So in other words, angular momentum is equal to the moment of inertia multiplied by angular velocity. Notice how this is similar to our linear momentum, which is equal to mass times linear velocity. And what you'll notice, whenever we tend to talk about rotational motion, I tends to typically replace m in terms of the linear counterparts, right? So wherever you tend to see an m in a linear formula, when it comes to the rotational side of things, you'll often see this moment of inertia pop up, right? Like we said, it tends to pop up quite a lot. That's why it gets given its own letter. We know from a linear point of view that mass tells us gives us an idea of what the inertia of a particular object is, right? We've spoken about it that the heavier an object is, the greater its resistance to its current state of motion. So if it's at rest, a heavier object is more difficult to displace. When a heavy object is moving, it's difficult to stop, right? The same principle applies with rotational motion. If this particular object is heavy, I have to apply quite a large torque to it in terms of force times the distance from the axis of rotation in order to get this object to start rotating. In a similar manner, so as this object starts rotating, and it's just constantly rotating or it's rotating with constant angular velocity, that means that the heavier that object is, the larger the torque is that I have to apply in the opposite direction in order to get this to stop. Okay, so very similar concepts that we're talking about here at the end of the day. Alright, so hopefully that makes sense intuitively somehow, right? I'm going to make a claim in the next sort of section. So the claim is as follows: that in a similar manner to which linear momentum is conserved, I claim that angular momentum is also conserved. Right? A really important concept to be able to unpack, because it applies to a lot of real life situations. I mean, you guys would have seen it in gymnastics, you guys would have seen it in diving, you guys would have seen it in parkour, you guys would have seen it in ice skating, so on and so forth. So I'm going to try and make some sense of it. So say, for example, I have, let's say, just have this circle over here. I have an object that is a certain distance from an axis of rotation, right? It has a mass of 10 kilograms. Excuse me. It is a distance, if that was r, of 2 meters from the axis of rotation, and it is rotating with a constant angular velocity of 10 radians per second. Okay, so therefore its angular momentum, which we stated up here, over here, is going to be equal to mr squared times angular velocity, right? So I can just plug in my values. That states that the mass is 10, the radius is 2 squared times 10. So 10 times 10 is 100, 2 squared is 4, so I'm sitting with an angular momentum of 400. And what are our units? My apologies. Well, mass is in kilograms, distance is in meters squared, so I'm sitting with kilogram meters squared, multiplied by radians per second. Well, radians is a unitless number, so this just simplifies to kilogram meters squared per second. Okay, it doesn't have a special name like a Newton or anything like that. We can just leave it in that format. Okay, so what we're assuming here is that this object is rotating and is constantly rotating, right? When the net torques acting on this object is equal to 0, that means that the angular velocity is going to be constant. In the same manner that when we talk about net forces, when the net forces are equal to 0, it means that the velocity of that object is also going to be constant. So notice how these are basically equivalent. In other words, it's saying that there's no force. If this object is rotating, there's no force acting on this object to keep to change its angular rotation, and there's no force trying to stop it. It's just rotating with constant motion. Okay. So part of this claim stating that angular momentum is conserved basically states the following: that the final angular momentum is then going to be equal to the initial angular momentum. And why would this be of any importance to us? Well, say for example that the following scenario happens. If this were, for example, my arm, and let's say I bring this mass a little bit closer as it is rotating, right? In essence, what I've done is I've decreased r. So let's say, for example, I bring r down to 1 meter. I've brought it much closer to my axis about which I tend to be rotating. What's going to happen to the angular velocity? Well, I'm not changing the mass itself. All I'm doing is changing how the mass is distributed relative to my axis of rotation. So, well, we already calculated what the initial angular momentum is. I'm just going to take this up here to give myself a little bit more space. So the initial angular momentum was equal to 400 kilogram meters squared per second. Okay, must equal, and I'll just give this a slightly different color, maybe let's go with purple, must equal whatever the final angular momentum is, right? There's no angular momentum that's lost. So since angular momentum is going to be equal to this mr squared times angular velocity, what we're saying is all I've changed is how this mass is distributed relative to my axis of rotation, and as a consequence what tends to happen is angular velocity will have to compensate. So if I just plug in values, mass is still 10 kilograms, r squared is now 1 squared, I brought it closer, so what's my final angular velocity going to be, right? If that's still equal to this 400, which it was prior to me initiating that change. So then WF, or final angular velocity, is going to be 400 divided by 1 squared is 1, and 10 times 1 is 10. So that's going to be equal to 40 radians per second. Okay, so let's just try and make sense of this for a second. So it's saying that I was rotating with constant angular velocity, right? And then what I started doing is bring, let's say for example, my arms closer to my axis of rotation, right? There were no other net torques acting on me at all, so nothing from the outside was trying to speed me up or slow me down. I was just rotating. Say for example, if I was an ice skater, right? And all I've done is brought my arms closer to my axis of rotation, and in so doing, the rate with which I tend to rotate has increased, right? So in essence, I halved the distance, but what happened is that my angular velocity has increased by a factor of 4. Really interesting, right? So I've quadrupled the rate at which I tend to turn simply by decreasing the distance that my arms were from my axis of rotation. So that's a really, really important concept. You see that in ice skating and in diving all the time. By bringing my limbs closer to the axis about which I tend to rotate, I can increase the speed of the rotation. So just to kind of make sense for that one final time, notice that when you have these people on diving boards, right? So they about to initiate the dive, so they would have some kind of initial angular momentum as they initiate the dive, right? Their goal is to rotate and complete a certain number of flips. So when they're in the air, what they tend to do is they tuck their body in. So what in essence that does is it decreases the inertia, right? So the moment of inertia. So it's saying that how the mass is distributed from an axis of rotation, I'm decreasing this radius component. So this person will continue to rotate and they still tucked in, and to compensate for this decrease in the moment of inertia, the angular velocity, the velocity with which they can rotate, tends to increase, right? And then as they prepare for entry, for example, in the dive, their body straightens out again. So here the inertia again increases, their rotation as a consequence of that tends to decrease, and they make a good entry into the water. Okay, so overall the angular momentum final over here is going to be equal to the angular momentum that it was initially over here. And if you had to plot that on a graph, what you'll often see is that since angular momentum is going to be a combination of the rotational inertia and the angular velocity, what you'll see is at the beginning there's going to be quite a large inertia, and then as they tuck, the inertia drops off to a minimum, and then as they start straightening out again, the inertia starts to increase, right? As a consequence to that, the angular velocity is quite low in the beginning because inertia is quite high, but then as they tend to tuck, so just trying to change color here, as they begin to tuck, the rotational velocity tends to increase, and then as they straighten out again, it starts to drop off. And overall, the angular momentum is just going to be conserved the entire time. It's going to stay like a straight line. Okay. And hopefully that all makes sense. So the really important part here is when we talk about angular momentum, the key to all of this is the moment of inertia and the angular velocity. As one tends to increase, the other one tends to decrease in order to conserve the angular momentum of the system. Alright, so that's a brief introduction. Hopefully I haven't confused you guys too much, and we'll work through quite a few examples of this because there are many applications that are incredibly useful in the world of biomechanics. Great stuff, thanks.